seen the title of this talk are probably a little baffled by it, Heterogeneous Hush Puppies. And I must confess that that outcome was somewhat intended. I wanted the title to be intriguing to stimulate your interest and your attendance. But at the same time, I may have been guilty of being too clever. So I want to use this opportunity to exonerate myself. Really what I intended to do in this talk was talk about our effort to make heterogeneous computing, that is parallel computing on a CPU and a GPU, pervasive. And we wanted to do this a little differently. We actually wanted to use principles enunciated in the book, The Tipping Point, the book that made our keynote speaker famous, Malcolm Gladwell, the book that talks about creating epidemics, and we do want to create one. So we wanted to use principles from that book. And if you've read that book starts out with the theme of hush puppies, the classic suede shoes with the crepe soles. Hush puppies are the poster child of the tipping point. In '94, they sold 30,000 units. Because they reached the tipping point, they sold 500,000 units in '95, 1 year later, and 1.5 million in '96. Those are numbers we like. And so in naming my talk Heterogeneous Hush Puppies, I was really making sure I gave Malcolm Gladwell his due. So I hope you forgive my indulgence. So now let me go into the theme of my talk. I want to use tipping point dynamics to describe how we move the industry towards a pervasive heterogeneous programming model. A tipping point is really the beginning of an epidemic. It's all the forces in place which allow that process to just flourish and spread, like a virus, a bad thing, or pervasive heterogeneous programming, a good thing. So if you look at the book, there are 3 rules, and they're very simple rules: the law of the few, the stickiness factor, and the power of context. So the law of the few basically is the idea that a handful of people can create a global trend, can change the world. This should not be that surprising, because if you know this famous quote from Margaret Mead, she says, "Never doubt the power of a small group of committed, thoughtful citizens to change the world." And then she goes on to say, "Indeed, it is the only thing that ever has." So this is not new. So in terms of tipping point dynamics, what are these characteristics of the small group of people that make such change possible? First, connectors. Connectors really are the networkers, the people who know lots of people, but they know people from different walks of life, different backgrounds. And that's what allows them to connect. There's a famous experiment by the psychologist Stanley Milgram, where he gives 160 people in Omaha envelopes, and he gives them a stockbroker in Boston as the destination, and he tells them, send these envelopes to those people who can move that envelope towards the destination. Most of the envelopes, it turns out, do reach that stockbroker in Boston, but the amazing thing is, half of them reach through just 3 people. These are the connectors. And these connectors exist in every milieu. Then there are the mavens. Now the connectors connect you to people, the mavens connect you to information. When I buy a car, I call my friend John, a very good friend of mine, who builds engines. He watches every model. He just loves cars. And not only does he research cars, but he also loves to give you the knowledge he's accumulated. He does it for altruistic purposes just because he enjoys knowing about cars. So he's my maven if I ever want to buy a car. I just bought one 4 months ago. I called him. And so everybody, sociologists estimate about half of the population knows a maven. So these are the people who give you the opinion, and that opinion is credible. And then there are the salesmen, the powerful persuaders. So if you look at it, the law of the few is that a handful of people who belong with these, who have these sets of features, can essentially change the world. That's the model we used for changing the industry to parallel programming. Then there's the stickiness factor, the second principle, and that is the fact that we're all bombarded with hundreds of messages every day. And so for a message to stick, it must be memorable. And the example that I'm giving you is very simple. In Yale University, there was this drive to have their seniors inoculate themselves with tetanus shots. So they developed a 7-page booklet where they described to them the horrors of tetanus, the seizures you can get, maybe the tracheotomy, and they create 2 versions of the booklet. One which talked about this in words, I'll call it the low fear version, and one that showed you this graphically with pictures in color. So that was the high fear version. They distributed to this to several Yale University seniors. And of course, when they did a survey afterwards, the high fear people said they're very motivated to go to the campus health center, which was described in the booklet, to get the shots. But only 3% of the people actually did it from both categories. And then somebody had this brilliant idea which changed that number from 3% to 28%. You know what they did? They inserted a single page in that booklet with a campus map and circled the campus health center and talked about the times when the tetanus shots were available. Now remember, these were seniors. All of them knew where the campus health center was. But it was just the proximity of that information which they made that message memorable and changed 3 to 28, a factor of 9. So subtle differences in presentation are really important. And lastly, the power of context. In the power of context, there are 3 aspects to it. Epidemics are sensitive to the environment. Those of you who remember New York subway systems in the 80s know that it was not a place that tourists like to travel in because there was a lot of petty theft, there was a lot of intimidation. It was completely changed sometime in the mid-80s. And the authorities, what they did first was eradicate graffiti. Because once you eradicate graffiti, it shows you a nice environment, then you can eradicate the other problems. Immediate context is really important. And here I have another example, and this time from Princeton University, from the Theological Seminary. So here they took a group of seminarians, and these are people who are obviously very altruistic. They devote their lives to their fellow men. They divided them into 2 groups. One group was told, both groups were told, you have to give a presentation at this auditorium a few minutes away. But the first group was told, you're running late. The second group was told, you have a few minutes, but start right now. And the experimenters, they placed in the middle a person who was bent over, wheezing, groaning. Clearly, somebody needed help. And guess what? The people were told that they were late. Only 10% of them stopped. And remember, these are seminarians. So these are really altruistic people. The other group, it was 65%. So the power of context, the fact that you're late overwhelms all your moral principles, and that determines what the power is of that message. And lastly, small groups are important. And the best example of this is the success of this book called The Divine Secrets of the Yaya Sisterhood. It was written by Rebecca Wells in '96, sold 15,000 units. Now this book is very emotive, very complex characters. In fact, the ideal book for book clubs to read. And very quickly the book clubs, it became the book club's book. And 2 years later it became a bestseller, selling over 3 million copies. And guess where it became a bestseller first? San Francisco. That's where the biggest density of book clubs is. So we decided, let's take these principles and apply them to the problem we are interested in, which is to make heterogeneous parallel programming pervasive. So who's our audience? If you look at software developers over the world, there are different ways of estimating it. There are probably a few million off. I did a fair amount of research. It's about 17 million plus 3 million students. So 30 million people who can program, most of whom will program for a living. So that's the audience. It's not small, but they are a community. They all make a living or intend to make a living from software. So this is the group that we wanted to address with changing the way they program. All of them know how to program CPUs, sequential processors. We wanted them now to also learn how to program parallel processors, that is graphics chips. So let me step back and tell you why this is important to AMD. AMD bought ATI in 2006, and if you look at the graphics industry, there are 2 companies, NVIDIA and ATI, which make graphics chips. And both companies realized in the early 2000s that these processors, which are an order of magnitude more performant than CPUs, and we should know we make both CPUs and GPUs, they're hardly used by any programmers. The only programming community that uses them, video game developers. And so both companies said, we better change this. Now NVIDIA was more innovative, and they created this API, this programmable API, which allowed you to use that order of magnitude more flops in a GPU, and they put it out into the marketplace. It was called CUDA. The only thing is, they were an aggressive company. CUDA only ran on NVIDIA GPUs. Now, NVIDIA and ATI are about half and half, for the market. And so while this approach worked fairly well, it had all the innovators and the early adopters bought in. Yet, if you're a company and you want to do something significant, you really don't want to do it on a proprietary processor. So the industry saw that, this was about 2007. So the industry saw that GPUs are now programmable and you get sometimes 5x, sometimes 50x improvement over CPU, sequential programs. So clearly value to everybody. So Apple, NVIDIA, AMD, Intel, ARM, IBM, every processor manufacturer in the industry got together and created an industry standard API called OpenCL. And the thing is, CUDA and OpenCL are very similar to each other. In fact, you can write a source-to-source translator from one to the other. But they are different, and that difference is critical. So our goal was, first, how to unify the industry around this new API, OpenCL, because that allowed it to run on our processors and, frankly, everybody else's. So that was our challenge. So what did we do? As I said, we decided, and this was a little, I wouldn't say controversial, surprising to most people because you don't think of an approach that sells hip shoes as an approach that would work for parallel programming. But we decided to try it anyway. And so first we decided who are the connectors. So here we looked at general developer conferences, general developers and general developer conferences. And I use the word general in capitals because when you do parallel programming, say in CUDA, they went after all the workloads that necessarily lend themselves to parallel programming, like computational fluid dynamics, quantum chromodynamics, all the high-performance computing applications. But there you're narrowing your interest to a niche group of programmers. We decided to go after Java programmers, open source programmers, because they talk to all the other programmers, and so we decided that the connections through them were higher. We actually did a Java version where the programmer can use traditional Java, but under the hood, we parallelized it. Now, the thing about OpenCL and CUDA being close really helped us because CUDA was still prime in the minds of those innovators and the early adopters. So we wanted to make sure that they knew that CUDA and OpenCL were very close. And that's a recurrent theme that we used throughout the campaign. Who were our mavens? They were the research analyst companies like Evans Data Corporation, who essentially look at the software industry and give the rest of the industry a view of what is hot, which languages are people using. Is it Ruby? Is it Python? Is it C? Is it, people like that? Then open source developers. These are really important because, open source, they're very righteous. And because they're so righteous, the rest of the community treats them as very credible. So if you have an open source developer or that community bought in, you probably got most of the software developers bought in. So we paid special attention to them. The big open source developers in x264, in Handbrake, in VLC, these are large communities. So we made sure that they all knew and they bought into OpenCL. And then, of course, there are the traditional software powerhouses. Sony, Corel, Arcsoft, Cyberlink, all of them we made sure that they used OpenCL and they announced it to the industry so that everybody felt comfortable about people using this new API. And then we had ARM and Intel announce last year that they were going to use OpenCL. So now if you look at it, AMD, NVIDIA, ARM, and Intel supported it. So if you are on any processor, whether you're in the low power space, the tablet space, the PC space, or the server space, which other processor vendor is there? So now we had that true pervasiveness. And of course, CUDA was still plugging away, talking about the value of pervasive heterogeneous programming. And finally, our salesmen were the top computer science professors. We made sure we got some of the top compiler experts, some of the top parallel programming experts in university talking about OpenCL. And university people loved it because this was finally an open standard as opposed to a proprietary approach. And then in AMD, we created a VC fund, the Fusion Fund, which I manage, where we essentially invest in software companies that do innovative parallel programming business models. And by doing that, I talked to a lot of VCs. Now they realize that parallel programming is an important workload. It can create a new business model. So those are some of the ways we subverted the tipping point models to making OpenCL work. The stickiness factor. The stickiness factor actually was easy. Here we had to distinguish ourselves from CUDA Because what's the difference? They're essentially the same. But OpenCL works on all those processor vendors. CUDA works only on NVIDIA. So we just had to highlight this. And that's a very sticky message for developers. Because if I'm a software vendor, I want to make money from my software. I don't want to be constrained to working only on one proprietary platform. It's an easy message, very sticky. And then finally, the power of context. The power of context, what we did is, one of the things that graphics chips do, besides having an order of magnitude more performance than a CPU, is there's 6 to 8 times more performance per watt. And in these days, when power and battery life in the low power space and heat sinks in the server space are important, reminding developers that if you want the same computation done with much less power, use a GPU is important. That was a very important message that we did, so that developers knew that they have a problem with having an application on a tablet run long, use the GPU. Then we had this textbook written by David Cayley from Northeastern University, one of the top parallel programming people in the world. So anybody who wanted to learn OpenCL had access to a textbook. Universities love this. 140 departments have already adopted OpenCL now. And so that's a big movement in the industry. And then lastly, there is still the CUDA attractiveness, which we just subvert to OpenCL. So that was our model for taking an existing paradigm, which unfortunately did not work everywhere, and bringing it as an open industry standard. So this is today's VHS versus beta battle that we fought. And so I'm happy to report that the results are pretty good, and that is my next slide. So in June of this year, there was a survey conducted by Evans Data Corporation, one of the top software analyst companies. So these are the results. In North America, OpenCL is the second most used multi-threaded API. Now, the first one is Intel's thread building blocks, which is not really a heterogeneous API. It's really used for, it's libraries that are used for multiple cores. So in a sense, OpenCL is the most prevalent heterogeneous API in North America. In the EMEA, again, it's number 2 to OpenMP, which again is a message passing open standard for running clusters of servers. So it's not really a heterogeneous API. In APAC, again, number 2 to OpenMP. So what these results show, and these were significant surveys, about 1,000 developers in each geography. So in the space of about 18 months, OpenCL was really nowhere in 2009. So by 2011, it's far ahead of CUDA in terms of getting developer mindshare. So I would say that in terms of our first goal, which is making OpenCL the #1 heterogeneous programming API today, we have been successful. But this doesn't mean that we've reached the tipping point, because now that there's a unified industry API, what we need to do is show the developers, those 20 million odd professional and university programmers, that there is value to using parallel programming, which today, given the kind of instructions we've had when we were students, is a little more difficult to use than, say, standard C running on a CPU. Show them that value. But what we've done is eradicated the VHS versus beta debate, which is corrupting that issue from progressing forward. So in terms of the tipping point, we haven't reached there, but we've made it a lot more likely that parallel programming is going to be pervasive and going to make a difference to end users everywhere. So that's what I wanted to say today.